Welcome back to the course Advanced Algorithms. We are continuing today and we are going to see the chapter 3 of the textbook, Competitive Programming 3, and this chapter is entitled Problem Solving Paradigms. In this chapter, we will see today the first part, which is the paradigm of complete search, also known by the brute force paradigm. We will see this part. It is in its turn divided into two main parts, the iterative complete search and the recursive complete search, and will be ended with some important tips on how to code for competitive programming. In each of the iterative and recursive sections, we will study them using examples and well-known problems, and we will see how to proceed, how to think in order to obtain optimal solutions. First, let us introduce the overview and the motivation of such a chapter. We need to master the problem-solving paradigms in order to be able to attack a given problem with the appropriate tool. We cannot have only one tool and solve all the given problems with this unique tool. Let's take, for example, four simple tasks to be performed over an array. Given that the array has n elements, where n is less than 10,000, the value 10,000, and each element is a small integer which is less than 100,000. So, for example, to be simple, let's to visualize the problems. Let's take A, the array equal 10, 7, 3, 5, 8, 2, 9, and it is obvious that n here is 7 and the values are given and they are not sorted. So four kind of problems. The first is, for example, let's consider we want to find the largest and the smallest element in A, in which case here they are 10 and 2. Let's consider another kind of problem. If you want to find the k's smallest element, for k equal 2, for example, so we want the second smallest element after 2 comes the value 3. Another kind of problems, if we want to find the largest gap inside this array. The largest gap is defined by x and y elements of A, such that the absolute difference between x and y is the largest, and here the largest gap is 8. And the fourth problem is to find, for example, the longest increasing subsequence, and in increasing subsequence we can find here 3, 5, 8, 9, which is the longest increasing subsequence. So for those problems, are the brute force algorithms all a solution for the four kinds of problems? For example, to find the largest and smallest element, you must iterate the array only once, and it is of complexity order of n, the size of the array, and you have to perform a complete search. For the second kind of problems, if you want to find the smallest and replace it with a big number, and then find the smallest and replace it with a big number k times, and then you found your k's smallest element, but this solution is a little bit complex, because for example, for k equal n over 2, you have reach order of n to the power 2. A better sort than choose the case. So one would say, why not sort the element using an efficient algorithm and then just directly take the case element in this sorted array, and this will give us the order of the best sorting algorithm, which is order of n log of n, and this is called divide and conquer the problem, and this is another paradigm we will see later. And better yet, solution also with divide and conquer we will see that we may have solutions of better per complexities. For the third kind of problems, if you consider to take each and every pair inside the array and just compute the difference, the absolute value of the difference, this is the brute force. Is this a feasible solution? It is order of n to the power 2, and this is a very large solution for n being 10,000 elements. One would think directly, but the largest gap is nothing else but the difference between the largest and the smallest element, and this is an order of n, and this is called a greedy paradigm. So you just have the idea and apply it. And the first kind of problems to find the longest increasing subsequence, you can try all the 2 to the power n possible subsequences, but this is of course not feasible for all n, which is up to 10,000 elements. So there exists another solution with the order of n to the power 2 in dynamic programming, and better yet in greedy, which is order of n log of k. An advice here is do not just memorize solutions. Whenever you see an explained solution in the book, just remember and internalize the thought process and not the solution itself, and the problem solving strategies that are used, so you can reproduce this process later. So we begin our first paradigm, complete search. So the complete search, also known by the brute force, includes also the recursive backtracking, which is a very well known technique called recursive backtracking we will see today. And it consists of, as the name complete search indicates, to traverse the entire or part of a search space. And during the search, you are of course allowed to prune. It means to not explore some parts of the space, judging that it will not lead to an acceptable solution. Develop this complete search solution, you develop it when you clearly have no other algorithm available. For example, when you are clearly asked to enumerate all permutations of the range less than n, between 0 and n minus 1. So you have to do it, and this is of the complexity factorial n. And we have better algorithm to solve the problem, but the input size is very small, so it will not perform as fast as simply a complete search solution. And with a complete search solution, you will have always a good answer, but you may have a time limit, so you may exceed the time limit, but you will never have wrong answer. So what you have to do is to calculate your complexity, and you see if the number of operations is acceptable. So go ahead, implement the complete search solution, because it is a faster solution to code, and if the time limit is acceptable, so go for it. And here is a table to show you. This is a rule of thumb time complexities for the worst acceptable algorithm for various single test case input sizes n. So here you have the n input sizes, and whenever n is less than 100, 400, 2000, etc., and you have to see if your algorithm, this is the worst acceptable algorithm. So for example, let's say if they tell you that the input size may be 100, and so the worst algorithm you may write is order of n to the power 4, because bigger than that, your solution will exceed the time limit. So for example, of n to the power 4 dynamic programming with 3 dimension, plus an order of 1 loop, plus for example combination of k elements among n, etc., etc. So if, for example, they told you n is can be 100 million, so the only thing you can write is an algorithm that of order of 1 or n or log of 2 log of n on the base 2, because you have to remind yourself that your CPU most probably can compute 10 million items in 3 seconds, and above that the time will of course exceed the limit. We begin the iterative complete search part with two nested loops problems, like the problem UVA 725. Here I gave you the link directly to it, and which states, the first part of it states the given, and this UVA is entitled division, and you can read it, or you can read this abridged problem statement, which summarizes the problem. So we are asked in this UVA to find and display all the pairs consisting each of 5 digits, such that the first divided by the second is equal to a given number n, and n is between 2 and 79, in which each letter is a different digit. So that's why we are going to represent them by the first number is going to be called, instead of X, it is going to be called ABCDE to refer to the 5 digits it contains, and the second number FGHIJ. And they say also in the given that the first number can be a 0. So the first number of either one of them, because it must be unique, the 0 digit must be unique in the appearance, so it can be a 0. And they also give us sample inputs and outputs, and here they gave us 2 inputs, and the 0 is for termination, and for the input 61, so for n equals 61, there is no such two numbers where the division is equal to 61 and where the digits are unique. So we have to display there are no solutions for 61 point, and a line separation. And for the second case, for 62, in fact there are two numbers where their division is equal to 62, so we have to list the two solutions and ordered by the numerator, or even the denominator, which is a constant fraction. So here we have 79546 divided by 01283 equals 62, and pay attention to the 0, it must appear in the number, and the other solution is 94736 divided by 01528 is equal to 62. So our job is to find all the pairs. And here we go, we are going to begin thinking. Since this is a division, and the division of the numerator over the numerator is equal n, first analysis will give us that this is 5-digit number, so it must be contained between 01234 and 98765, which are the smallest and biggest numbers composed of 5 digits. So first of all, our complete search is limited to 10,000, to 100,000 operations. Okay, and this is a first bound. A better bound would be to know that this is a division, a fraction. So, and each of the numbers is 5 digits. So also ABCDE is composed of 5 digits. And the maximum that ABCDE can take is also 98765. So, and divided by FGHIJ will be equal to n. So divided by n will be equal to FGIJ. So FGHIJ is limited therefore by the maximum number divided by n, and always bounded by the it is forcefully greater than the minimum number composed of 5 digits. And therefore If n is big, the number will be small. So the biggest number here is for n the smallest, and they already told us that n is equal to 2 and up to 79. So for the smallest n, we have the biggest scope of search, and which is now 50k. So this is good. So what we are going to do is that we are going to search for the denominator in this scope, and for each FGHIJ we can find ABCDE by multiplying FGHIJ by n. And then we have the two numbers. We have to check whether the two numbers are both composed of unique digits. Okay, so if they are composed of unique digits, so we simply list this solution. So the number of operations will be 50Ks, and plus for each round we have 10 operations to do in order to test whether the digits are unique or not. So this will give us a 500,000 operation per test case, which is considered a small number of operations, and in this case the complete search can give us a solution. So before we explore and explain this solution, here we are going to use a bitmask, and I will introduce the bitmask and then go back to the solution. So the bitmasks are lightweight small sets of booleans, and they are, whenever possible, used in integers. So integer can be considered a sequence of bits, and bitwise manipulation is more efficient than a manipulation over an array of booleans, etc. An example how to use this, consider this, the S value is 42. In binary, it is 101010, and this value can be used to represent the set BDF in the subset BDF in a set A, B, C, D, E, F. So if I have A, B, C, D, E, F a set, and I want to say that, for example, the elements B and D and F are used, I just set the integer value as because the binary representation of S sets ones inside the elements. Or I can use this as an element of order 0, 1, 2, 3, 4, and 5. And so I can have also a numerical indexes for the elements. And then if I want, for example, to say that jth item, I want to turn it off or on. If I want to turn it on, I just do an OR, a bitwise OR operation. So S will be equal to S or 1 multiplied by J. So 1 less than, this is a left shift of how many digits of J digits. So I go, this is digit 1, 0, 1, 2, and this is digit 3 for J equals 3. So I am going to do the decimal number 8, which is the binary number 1000, and then I say S or equal, it means S equals S, or this number J, this number, which is 0, 1, 0, 1, 0, 1. So, and the AND operation is 0, 0, 0, and wherever there is two ones, it will be 1, and this is an AND operation. So here we are seeing the common elements between two sets, and we have only D. In order to play a little bit, we can go to the visual representation, to the visual animation, and we can set as whatever we want. For example, I set as 43. So here it goes. This is the number 43. And for example, I want to set the bit, which is 0, 1, 2. I want to set the second bit to 1. So check bit 2 to 1, and here we go, and I shift to 2 places, and here it is 100, and then I execute the OR operation, and now I have S, the initial, and the new S, where the bit number 2 is set now on. And you can try within this animation, beautiful animation, all the possible bitwise operations and bit manipulation. And bit manipulation is used in problem solving. So now I can know that I will use this operation in order to check for the uniqueness of the digits. How I will do this? I will take an integer to represent the set of the digits, and for the digit 0 I will place it in the least significant digit, digit 1 for the next, and so on until I represent 10 digits. And here our solved problem, division problem. So as we already said, we have to read the n, and if it is not the first line, I have to print f \n. This is C code, of course. And then I have to use a boolean, because if there is no solution, I have to print a special sentence: there are no solutions for this n number. And then I will take the double loop, the nested loops, and here we go. We are going from the lower bound to the upper bound, which is the biggest 5-digit different numbers divided by n. And every time, as we already have said, we are going to find the numerator, which is a multiplication by this number by the given n. And then all the rest here, we are going to do what? We are going to check for the uniqueness. First, we are going to put inside used every used digit. So used is going to be our bit mask. And first of all, for the digit 0, we want to know if it is used or not. So we take FGHIJ and we say if it is less than 10,000, then the first digit is 0, then it is used. The digit 0 is used, so I say used equal 1 if this condition is true and 0 if this condition is false. So we begin our bit mask by setting the least significant bit to 0 or 1, and the rest of course is 0, because this is 0 or 1. And then I begin our temporary value is now ABCDE, and then I will check it. So we continue, we take the first number, and for each of the digits, we are going to take each of the digits. So each time we are going to divide by 10, and then take the rest of the division, which is one digit, and check it using the bitwise operation we just saw. So we do shift left, how many times? The digit times, and we make an OR with the used, and the same thing with this second denominator. And then at the end we have inside used a bit mask in which we have ones whenever there is a used digit, and 0 if the digit is not used. And how do I know if this is unique or not? Because they are 10 digits, the used must be all 1. So if 2 digits are the same, then therefore there must be 1 digit not used in the other hand. So I compare the value of used to 1 shifted to the left 10 times, minus 1, and this gives me all 1. And if it is not all 1, then um, the uh, the digits are not unique. If they are all 1, the digits are unique, and therefore I will print the solution. Attention here, to in order to print the 0 in front of the number, and this is a percent %d, I am forcing the 0 printing, and I am forcing 5 digits printing, so you will complete with 0 whenever it is less. And this is it. I pay attention also to the spaces before and after the equal and before and after the division operator. Another kind of nested loops with many nested loops problem. We have the UVA 441, and which is called Lotto, and which states that we can take a subset of a given set and choose 6 numbers among. So the simple loop is easy, and you must master the nested loops, which are, I am sure you do. The abridged problem statement is given k integers, where k is less than 13 and of course greater than 6. You have to enumerate all possible subsets of size 6, so all possible subsets of size 6 of these integers among k integers, and the integers are not consecutive. So you have to list them in sorted order. So what shall I do? This is also a complete search problem, and I have to test my computational complexity. So this is six nested loops, and the largest test case is when you give me k is equal to 12. So this is a combinatory. I have to choose 6 amongst 12. How many subsets I have? I have 924 cases, which is considered small and feasible. So I write the complete search solution within, I read the number and I read the digits, and then I 6 nested loops, and it must be in increasing. So always I begin from the lower bound, and then I have to print the numbers which I stored in the array S. Another kind of iterative complete search problems is where you have loops, but you can have also pruning. So there are cases that you can eliminate. We consider UVA 11565, which is called simple equations, in which you have 3 equations and you have 3 known numbers, and you have to find x, y, and z. And the abridged problem statement says, given 3 integer ABC in between 1 and 10,000, find 3 other distant integers x, y, and z such that the sum of them is equal to a, their product is equal to b, and the sum of their square is equal to c. So we begin, of course, we can know first that we have 3 nested loops, but from where to where should we start to find x and y? The third equation is a good start. We can say that if C is bounded by 10k, and let's say what is the maximum value we can find for x, it is, if we eliminate these two terms, if we consider y and z almost 0, they cannot be 0 both, they have to be different, we will have x to the power 2 equals c, which will give us x is in the range of minus 100, 100. And we apply the same reasoning for y and z, and so we deduce that the 3 nested loops must go from minus 100 to 100 for a complete search of x, y, and z. But We calculate the operations and it is feasible since 2001, 201 to the power 3 is 8 million operations. You can implement this and you can add to the loop the short circuit of a lightweight check. So you are going to find three different numbers. So if they are not different, so you just jump and uh, they have to apply, they have to satisfy the three operations, their sum, their product, and the sum of their square. Although this kind of solution may pass, we can improve it by providing a better solution in considering the first two equations. If we see that the sum of the x, y, and z is equal to a, so we remark if x gets bigger, y and z must become smaller. And then we see we look to the product that would have to be equal to b. And since in the given they told us for different solutions, choose a solution with x smaller than y smaller than z. So we have this constraint already, x less than y than z. So the maximum value that x can take is at the best y and z. So if we replace, we shall have that the product of x by itself 3 times is less than the product of x times y times z, and therefore less than b. And we can conclude that x is less than the cube root of b, where b is at its best equal 10k. So x is in the interval of minus 22, 22 because the cube root of b is 21 point something and x is integer. And I have now x is going from minus 22 to 22. And I continue the pruning, so not only x is going to go from minus 22 to 22, and I have to not find a solution, and I continue pruning with if the square of x is greater than c, is greater than c strictly, I stop searching because I didn't find yet y and z that they must be bigger than s. And then before also after the second for nested loop, I have also to continue pruning to see if the same thing, x times x plus y times y, is still less than c, because if it's greater than c, I have to stop. This is not a feasible solution. And after the for z loop also, I have to check whether I am checking for different x, y, and z. And at last, I check for the three equations. And in case everything is okay, I print and I say that I found a solution. Another complete search iterative problem is the problem of permutations. We consider the UVA 11742 called social constraints, and it talks about placing people on seats with a certain constraint. So some people don't want to sit beside others, and on the opposite hand, some people want to sit near others. And the abridged problem statement is that there are n moviegoers, so we have n persons given n less than 8, and they will sit in the front row, so they will sit in consecutive seats. And there are m seating constraints, so maybe m is up to 20 constraints among these persons. So the constraint is of the following format: A, B, C, and it means that moviegoer A and moviegoer B must be C seats apart If C is positive, they must be at most C seats apart. So the difference must be less than C. And if C is negative, they be at least C seats apart. They have to be at least, so the difference must be at least C or bigger. And the question here is given n and m and the m constraints, how many possible seating arrangement can we have? So we have to permutate to calculate all the possible permutations of seating arrangement, and for every arrangement I have to see whether it is a good arrangement or not. So the key here is to explore all the permutations, which are of the order of n factorial n times m, because every time I have to check for the m constraint, and the largest case is for 20 times factorial a, and I set the counter to 0 and I do the permutation, and if this permutation satisfies all the m constraint, I increment the counter and so on. So here is the C solution, and in the C solution you see it is very easy. You do the permutation and you have a do while, and inside the do while, of course, first you read m and n and all the constraints and you store them, and then you do the permutations, and for every permutation you check whether it is compliant to the solution. So if C is positive, you see if the difference is less than C, and if it's negative, you see is greater than C, and if all is okay, you increment answer. But what is next permutation? So how to permute? I will explain how to permute in the next slide for Java language, because for C language it is included in the library. For Java language, this is a very easy method that you can write. This is a static permute function that takes a list of items to permute of type T. So here you can give it any list type, integer, string, etc., and you permute it. So you take it, and how do we handle this? N is will play the role of the iteration number. So when the iteration reaches the size of the items, the number of the items, I handle the permutation. I have the full permutation. So for example, I count it, I display it, etc. And in between, what I do is I will loop inside the recursive call. I will loop because I want to do all possible permutations between n, the given index, and the following ones. So I want to permute n with n plus 1, n with n plus 2 until the end of the size of the list. And always I will swap I with n, where I goes from n to the end, and I will call the recursive call permute for n plus 1, and then I will swap back. Why I will swap back? Because for the next iteration, for the next four iteration in this loop, I want everything to be untouched, so that I can cover also all the cases. And how do I call this function? I call it with an initial value for n, which is equal 0, which is in fact the iteration 0. So let's continue with our permutation in Java and take an example. Let's take a very small list, ABC, and call the permute function given this list and the index 0. At index 0, I will not enter the base case. I will enter the else of the base case, which is the rest of the function, and I will go for I equal 0 until the end, I equal 0 until the end, and each time I will permute with I. So I will permute n, which is 0, with I. So I will permute 0 with 0, and then I will permute uh, I for I equal 1. I will permute it with n, which is 0, 1 with 0. In this case, um, I will have, instead of ABC, BAC. And in the last iteration, I will permute 2 with 0, so B will stay at its place. I will have CBA. And in each one, I have also recursive calls. So I have ABC, I have fixed A, and then from the second one, and from n equal 1 now, until the end. The end is a base case only because this is a list of 3 items. So I have A, B, C, and A, C, B. And when I switched the first with the index 0 with index 1, I had BAC. So I continue to next iteration with n equal 1, and I switch A with C, I will obtain BCA. So this is 4 of the 6 permutations, and the last 2 is for I equal 2, where I have CBA and I have also CAB. So here are the execution of this small Java example. Whenever you have to permute and to count the number of permutation, just copy and paste this function and handle here inside the base case whatever you want to do. If there is a condition, you shall put it here. So I will show you now what we did with our problem. This is the draft in Java. So we read N, we read M, and we fill the constraints. Okay, we fill the constraints. And now that we have the constraints, all what we have to do is we have the maximum is for N is 8. So I have this list from 0 to 7. And all I have to do is to take the sublist from this array, which is, for example, if n equal 4, I take 0, 1, 2, 3, for example. And then I will do the permutations. I give the initial value for n, which is 0 for n. And then I give m and constraints, the array of constraints, and the number of constraints in order to, inside the permutation, I want to handle the permutation. So to handle the permutation, I will not count it unless the constraint all apply. And I add here another function apply, which takes the list of items and the constraint and their number. And I say if the difference is greater than the constraint, in case the constraint is positive, so return false, and also if the constraint is negative, if the difference is less than the constraint strictly, also return false. And if you didn't return false for all the loop, then they apply to the constraint, so return true. And if you returned true, I will count this as one permutation, successful permutation, else I will not count it. And inside the for loop of the recursive function, I am counting the cases, and then I will print these cases, and I read the next text case and print it. So if we go back to our problem, now you know in Java how it is written. You should know that in C it is very simple, as I already mentioned. You just call next permutation and you give the end of the address of the end of the array. So he knows that he has to permute these elements. You give the address of the first array and the address of the end of the last element. And this is an example in C, and this is the output, exactly the same thing we got in Java. I go back to the slide of the UVA, the first slide where I showed you the problem, and here is the solution in C, which is exactly the same solution that you just saw in Java. So this is a problem that in which we dealt with permutations. We end the iterative complete search section with the following problem kind, which is subsets. And for subsets, we take an example, the UVA 12455 called bars. Here is a part of the UVA that we will read for it the abridged problem statement, and which says, given a list L containing n integers, where the number n is less than 20, and given x, so the question here, is there a subset of the list L that sums to another given integer x? So I give you the list, the n integers, and I give you x, and I ask, are there a subset of L that the summation of the subset is equal to x? And here again, you will find yourself in front of trying all the possible subsets. I have to try all the possible subsets of L, which are 2 to the power n. And sum each subset. You have also a complexity of order of n to sum. And to check if the sum is equal to x. So you tell me, yes, there is. So the complexity is n times 2 to the power n. And for the largest test case, n is equal to 20, and you have 21 million operation per test case, which is considered very large, but there is a trick that can make it viable via bit manipulation. How you are going to do the subsets? You are not going to enumerate them. You are going to use binary representation of integers. So in order to represent all the possible subsets, you consider every element, you have an element. So every element in a subset is either present or not. So if you consider it as a bit manipulation, you consider that there is n bits, and in every subset, either we turn on the bit corresponding to given element or we turn it off. So how many possible subsets we have? It is the different value we can have for n bits. It is 2 to the power n minus 1. So the values are, 2 to the power n, going from the value 0 to the value 2 to the power n minus 1. And this is our count, and this is our subset. How we are going to do? We are going to make a for loop from I equals 0 to I equal 1 left shifted n times, and this is 2 to the power n minus 1, and I plus plus, and we go sum equals 0, and if for j equals 0 to n, if the bit represented inside I for j, this time we have this many 2 to the power n cases. For each case, if the bit corresponding to j, which is the elements placed in the list, is on, so we just explained this, you sum the length of the element, and if it is off, that means it does not, this iteration, it does not make part of the subset, so we don't sum its length. And if the sum after the for loop is equal to x, we found a solution, and the question, is there a subset that sums? So is there a solution or no, not how many solutions there is. So once I find a solution, I directly break. So this is a With this problem, we terminated our first subsection of section complete search, and next is the recursive subsection. The second subsection of complete search is the recursive complete search after the iterative complete search. In this subsection, we will see the simple backtracking, which is recursive backtracking, and we will consider the UVA 750, which is the 8 queen chess problem. This is a very well known problem, and a bridge problem statement is as follow. So consider a chess board 8 by 8, and what is the problem? We want to place the 8 queens so in such a way that no attacks are possible. Here in the first figure I show you 2 queens, and each queen is on a different column, different row, and different diagonals than the other, so neither one can attack the others. So the problem here is we want to place 8 queens like in the second figure. This is a possible solution for them not to attack each other. What in this problem exactly is wanted given one queen position? So they give us a queen position, the integer position indexes of a queen, and we have to determine all the possible arrangements. يعني if they give us a queen, we have to determine all the possible places the other 7 queens can be in which, and if more than one possible arrangement is here, sort them in lexicographic order. And like this, they gave us the queen at place 1 1. First of all, we have to translate into 0 indexing. So we have a queen at place 0 0, and the solution is we have 4 possible solutions. If the queen at column 1 and line 1 stayed fixed, the queen at column 2 can be at line 5 and the others as follow, or at line 6 or at line 7 with 2 possibilities for the rest of the queens. So here this is the way they want the output, and we want to give the solutions. Before thinking about the output format, we have to think of how to find the solution. So the first thing we have to, if we consider complete search, so we will complete search. We have to choose 8 places for the queens out of 64. It means 8 by 8 cells, and this is a combination 8 among 64, and it will lead us to 4 billion possibility, which is not even worth thinking of. And the first insight will come. You will say that I will put 1 queen in each column, and in fact they told us that we have 1 queen in each column explicitly because they want a solution like this. So you say, if I choose the first column, what will remain is to choose the rows, and thus we have 8 to the power 8, and we reduced a big part the complexity, so it becomes 17 million. But this is not enough. We want to make more optimizations. So we continue thinking, and we say that because we want no attacks, we have no 2 queens can share the same column or the same row. So you find the permutations for row. You have every queen in a column, and you have, if you for the column 0 you chose the row 1, you cannot now choose the row 1 for the next queens. So instead of being 8 to the power 8, now it is a decreasing, it is factorial 8, and becomes approximately 40k operations. So this is fast. And for example, if I represent row of I equal R, I mean the queen in the column I is placed in the row number R. So here I have to find the row number for the given column. I have the columns I from 0 to 7 and I want to find the row numbers. For example, in the figure 3.1, the row numbers are 1, 3, 5 for q equal 2, 7, 2, 0, 6, and finally 4. More possible optimization can be made when we think that the queen can attack via the diagonals. So if I have queen A on the placement row I column J and queen B on the row K column L, if the difference in absolute value between I and K is equal to J and L, it means they are either on the left diagonal or on the right diagonal, so they can attack each other, so this is not okay. And if the difference between these coordinates in absolute value is not equal, so the queens can stay at their places. So we will proceed the solution by making a recursive backtracking. We start by placing one queen, and then we see if the next queen where it can be placed. And in columns from 0 to 7, we place the queens one by one, and each time we observe all the constraints, and if one of the constraints is not respected, we will disregard, we will prune this solution. So we check the candidate solution. We have to remember that they give us a queen coordinate and we give them the rest of the queen's coordinate. So if we find the solution, we find an absolute solution, and then we see if inside this solution we have a queen at the row B and the queen at the column B and a row A, and then I print the solution. And I am traversing the solution in lexicographic order, so no problem. Once I find it, I can print it directly. And this is a problem which is a sub-order of factorial n, and not even factorial n. This is less than factorial n because I'm eliminating cases, and this solution will of course take an accepted verdict. So before explaining this code, let us explain what is backtracking. So as per the definition in Wikipedia and in other better references, we say that backtracking is a general algorithm for finding all or some solutions to constraint satisfaction problems. So we have to find a solution, but we have a constraint problem, and to find this solution, we incrementally build candidates to solutions. So there is a way to build a candidate in incremental way, and while incrementally building this candidate solution, we can abandon a bad candidate. So I add a candidate. If I see that this candidate is not good, I can remove it. Okay, and this backtracking technique is only good for problem which admits a concept of partial candidate solution, and in which we can build the solutions gradually, and that they have also a relative quick test, so I can, while building, validate or not a certain partial solution. And this is a faster way than the brute force enumeration, of course, because in the beginning of the 8 queen, I told you the brute force enumeration will cost us billions of operations, 4 billion operation. So the backtracking is a better way, is a faster way, and because it eliminates as many candidates as possible with a small single test. And here is a representative. At the end of the tree, you begin with iteration 0 with as the initial case, and you start building you. So at every step of the process, you build your solution, and at the leaf level, you got your solution complete, and you can eliminate, you can prune um, solutions, and you can have complete solution as the schema shows. So back to the problem, to the solution, I will explain it here. So given the problem UVA 750, here is the solution after we have so, so together the possible enhancement. We read the A and B indices of the queen, of the given queen, and we decrease them by 1 to be in the zero-based indexing. And then we have already declared a global variable row in which we will fill for each column the row number for the queens in order to print it at the end. And then we will set this row to be equal to 0 at each iteration. We will fill them with 0 with memset operation. And then we will count the solution at we are asked to put the solution numbers, and we will begin backtracking by giving the column number 0. For the column number 0, of course we will not enter the base case because the base case is for column number 8. It means we finished all the first 8 columns, and in this case, in the base case, in case we reach the base case, we see if C is equal to 0 and the solution satisfies the input row of B equal A. In this case, what we have to do is only to print the solution, to print the line counter, the solution number, and to print the row of 0 and then row of 1 until row of 7, separated by spaces and backslash and at the end. So if we reach the base case, it means we reached the leaf level. It means we finished the placement of the 8 queens. We see if the coordinate of the given queen are inside our solution, we print our solution. Else, what are we going to do? There is also a for loop inside which there is a call to the backtrack itself. There is a recursive call inside the for loop. Why? Because we want to see all the possible permutations that satisfy. We don't want only one satisfying solution. So what we do for each r going from 0 to 8, and we have an early pruning if C equal B. So if we are at column C and the row is not going to be A, we don't trouble ourselves to test the solution because this is not an acceptable solution. So this is an early pruning. Else we continue. If I can place R at the if I can place a queen at the row R and the column C, what is I can place? It means it does not disturb with the previous queens. How do I do this? How I know if I can place? This is the backtracking. So I check the can place function. It takes the row and the column, and it checks the previous from 0 to the column, before the column. If any row is already occupied, if any queen has already occupied the row R, or any queen has the same left diagonal or right diagonal as the R and C, so absolute row previous minus R equal absolute previous minus C, because this is the column, If any, I will return false, and else I will return true. Here I have a small type mistake. I will correct while explaining. Okay. And then we will continue. If I can place it, so I place it. I put row of C equal R, and then in the same if, I call a recursive call for the backtrack next column. And when this finishes, I will reach a base case, and then after this base case, I will redo the same thing for the next row. So for a same queen, I can have multiple solutions. So this is a beautiful backtrack algorithm, and it is very well known. And here the comma is, notice the comma is because inside the if there are two statements without curly braces. And I recurse only if I can place it. If I cannot place it, I don't continue with the solution. And this is why we say that the solution is sub O of factorial n. Because whenever, the sooner I find that this solution will not lead to an acceptable solution, I will stop it. So I only backtrack, I only recurse only if there is a hope that I can succeed. Another more challenging backtracking problem is the UVA 11195, which is also another n-queen problem. And in this problem, if we read it, we can conclude the abridged problem statement, the following one: given an n times n chessboard, and this time not 8 by 8, n can be until 15. Uh, we want to place the queens, but some cells are bad. We cannot place queens on them. They will not prevent the attack, but they prevent the queens to be placed on them. So the question here is only how many ways to place n queens. Okay, we give you only the size of the board, the width of the board, and you tell me how many ways I can place the queens. And also the recursive backtracking here is not fast enough, because for n equal 14, suborder of factorial n is will be a very high number. So it is not possible. What was possible for n equal 8 is not possible anymore for n equal 14. So what are we going to do? We are going to change the can place operation that we implemented uh, in the previous problem, because in the previous problem we implemented an operation can place, and in which we were doing we were executing some instructions, and we will replace it by the idea that we will hold just like we hold it for each. We are proceeding by column, okay? So each time in a column we occupied a row, we hold the row number and we said that it is already occupied. This time we will remember the diagonal numbers that were occupied. And to do so, we will use the three Boolean arrays, one for the rows, one for the right diagonals, and one for the left diagonals. And initially, all the arrays are set to false, so any queen can occupy any cell she wants. And then we have n rows, and we have 2n minus 1 left diagonals and 2n minus 1 right diagonals. And when I place a queen RC in a cell, that means the row of R, okay, the row of R is true, is occupied and cannot be taken in a future iteration. And it means by a simple calculation here that I already showed you, if we remove the absolute value, we can obtain either this is equal to the negation of this or is equal to the positive value of this. So we can take C from the same side, and we obtain that the left diagonal number that will be occupied is LD of R minus C, and we add n minus 1 in order to have a positive index, and the right diagonal is of index R plus C is also occupied whenever I put a queen on the indexes R and C. And add to this condition the condition that was initially in the problem, that there are bad cells and we don't want to place queens on bad cells. So I add to all of this if the board of RC is not bad, so I allow the condition. So here how it becomes a backtrack function. First answer is a global variable in which I accumulate, and I don't forget to reset it for a next test case. And then I have the flag off whenever I have an if statement like this. So if the cell is not bad and the row is not taken and the diagonals are not taken, I can take them and backtrack for the next column and then set them off back. Why? Because I want to count all the possible cases. So I restore because this time we want to call all the possible cases. And here we can see a recursion, a very beautiful recursion animation. You click on it, whatever animation you want to in recursivity, to understand how the recursivity works. We finished this section, the complete search, by a set of tips that the authors of the book Competitive Programming 3 wrote and that I find very, very important. So I summarize them in those tips, and you can read in the chapter if you want more details. So tip number 1 is filtering versus generating. Filters are you can find the filters in the problems that we solve together today in iterative complete search, in opposition of generators, which are um, in the uh, in the backtrack recursive backtrack search. And of course filters are easier to code, but they run slower. But do filters instead of generators whenever you find it is possible. Tip number 2, prune infeasible and inferior search space early. When generating solution using recursive backtracking, the earlier you can prune the search space, the better. And you can, in other problems here in the backtracking problem for 8 queens, we prune the solutions that are infeasible or that are not going to give us the answer. But in other problem, you can also compute the potential worth, and if this potential worth of the current solution is not greater than the worth of the best found solution, so you can also prune it. Tip number 3, utilize symmetries. So for example, in the 8 queen problems, there are 92 possible solutions, but they are only 12 unique, and the others are rotations and symmetric solutions. So take advantage of symmetry whenever it does not exploit your time and it is not complicated. However, sometimes considering symmetries can complicate your code, so disregard this tip. Tip number 4, pre-computation aka pre-calculation. So sometimes in some problem you can find yourself in computing tables or other data structures and filling them in order to help you. And this is called pre-computations. And the later the solution comes is you already filled your data structure, so you can get the answer in a more rapid way. But this kind of tip is rarely used for recent programming contests, so you don't really need to make pre-processing. Tip number 5 is try to solving problem backwards. So some contest problem look far easier when they are solved backwards from a different angle. Tip number 6, optimize your code, and this tip contains 12 points and tricks to optimize your code. And in order to do so, you have to understand your computer hardware, the way it is organized, the input output, the memory, the cache. And those are the tips. For C++, use C and C++ better than Java because it is faster. And but you have to know that if you use Java, you get extra time by most of the judges. For input output, use scanf, printf. They are better than cin, cout. For Java users, you used buffered reader and buffered writer classes, and I provided here a skeleton that you can use in your programs, in your Java programs. You have your own scanner class, not the scanner class that we know. We called it scanner, but it is in fact using buffered reader. And tip 6.3, quick sort is preferred over heap sort. Point 4, access to dimensional array row by row because they are stored so inside the memory. Point 5, bit manipulation is better than array of booleans. Point 6, low level data types, bigger array than vector. So don't use vector directly, use a bigger array. And if you want 32-bit ints, and they are better than 64 longs because the operation are faster. Point number 7, in Java, for Java user, use array list and not vector, and string builder and not string buffer because vector and string buffer are thread safe, and in competition you don't need really this feature. Point number 8, declare most data structure global because this will faster the coding and you don't pass the argument to the functions. But don't forget for multiple test cases to clear and reset your global variables. And prefer iterative over recursive because it is faster. And point number 10, array access in loops. If you are not changing the element value, just store it in a temporary value. It is faster to read it if there are nested loops and you are using this value in many loops. And point number 11, in C, C++ macros and inline functions can reduce runtime, so they are faster than ordinary functions. And as for strings, C++ users, we advise you to use array of characters instead of strings of the C++ style string. And for Java users, be careful for string because string is immutable. String variables are immutable, so use the functions for string in a good way. And maybe sometimes you have to use string builder as already mentioned. Tip number 7, use better data structure and algorithm because all the tip number 6 points are not going to be good enough and not going to be fast enough if you are not using the right algorithm and the right data structure. And this is of course self-explanatory. Next week we will see the divide and conquer paradigm.